Hi, my name is Scott Simpson, and today we will be going over the example of how to calculate the structure factor for cesium bromide. So up here you can see the diffractogram for cesium bromide. Cesium bromide, if you look at it, is a primitive cubic cell that has the bromine in the center and cesiums at each of the points. However, since this is repeated, there is only one cesium per unit cell and one bromine per unit cell. So what we're going to do is we're going to calculate the structure factor of this system. So as our example, we have cesium bromide. There are two atoms in the unit cell, one cesium, and we're going to say the cesium is at the origin. And since we're using fractional coordinates, u, v, and w, u would be equal to 0, v would also be equal to 0, and w is also equal to 0, given that we're at the origin. And now the bromine, since the bromine's in the dead center of the unit cell, it has fractional coordinates of 0.5 for u, v, and w. Okay, so now let's go back to our original structure factor equation. And we know that the structure factor has the atomic scattering factor for each element that we're considering within the unit cell, times a term to look at where the atoms are in the unit cell and what Miller plane we're shooting our radiation down. So remember, structure factor HKL is equal to the summation of those. So we have to have a term for cesium and we have to have a term for bromine times e to the I2 pi. And remember, we got h times 0 because it's h times u for whichever element we're considering. Cesium's at 0, 0, 0, so we get hk times 0 plus L times 0. So that's the portion for the cesium. Now we got to add the portion for the bromine. So I2 pi h of times 0.5 plus k times 0.5 plus L times 0.5. Okay, we multiply that all the way through. Since it's all zeros up top here, we get e to the 0, which is just 1. So we get the structure factor of cesium. Next, we got to look at what it is over here. So we got 0.5 times all of these things and the 2 out front. Those two terms will cancel. And we're left over with I pi h plus k plus L. All right, we know from our last example that there's this interesting even-odd effect when we add up all the h's and all the k's for this term and how that changes, because this complex number right here can actually be thought of as a combination of sine and cosine. And since we're hitting values of pi based upon this, we will either get a -1 or a +1 for this term here. So let's summarize that. So let's write out our structure factor just one more time. FHKL, we said, is equal to this, plus structure factor, or atomic scattering factor of bromine, I pi h plus k plus L. And then we know from our last example, and we could easily show it by plugging values in here for different reflections that we see. Last example. H plus K plus L. We have odd situations and we have even. We would get the structure factor to either look like the atomic scattering factor of cesium minus the atomic scattering factor of bromine, or the atomic scattering factor of cesium plus the atomic scattering factor of bromine. Okay, so let's look at certain reflections in this diffractogram. It makes sense why we're seeing these big guys, because when we have even H plus K plus L, so for example, this would be even the value of 2, we get a very large reflection here. Same for all of these even valued Miller planes that we're looking at, because the scattering factors are adding to one another. However, in our previous example, when we had the structure factor of tungsten minus the atomic scattering factor of tungsten minus the atomic scattering factor of bromine, the atomic scattering factor of tungsten, they canceled each other out. However, here we notice we have some of these odd reflections. So why do they keep popping up? So first question we're going to ask is why do the odd H plus K plus L reflections show up? And really, the answer to that is the structure factor at these points is equal to the structure, or the atomic scattering factor of cesium minus the atomic scattering factor of bromine. And we know that these two things are not equivalent to one another. However, the closer that they get to one another in terms of electron density and electronegativity, we will start to see these reflections fade. So the more similar the atomic scattering factors, the less pronounced those reflections will be. Then if we have to compare which atomic scattering factor is larger, if we pull down the periodic table and we consider the electron density around these elements, what you can see is cesium has far more electrons, and if you consider its atomic radius, either covalent, ionic, or van der Waals, you will see that that one is significantly larger than the bromine. As these two values get closer to one another, however, you will start to see these reflections diminish. So that's what's going on with our cesium bromide example. Thank you for watching, and if you have any questions, please leave them below.